All right, good afternoon. I hope you had a good lunch break. So we will continue the session this afternoon. We have a couple presentations. The first one is by my colleague, Jana Dopa, who is an associate professor, Hoyt Roberts Endowed Chair, associate professor in the School of Electrical Engineering and Computer Science. Jana's main area is in AI and machine learning. And he's involved along with his students in the CySER program since the beginning. And today he would be talking about human in the loop anomaly detection. And as I have shown you in the chart I have today, this belongs to the AI and machine learning collection of topics. Jana, when you are ready, go ahead and get started.
Thank you, Asifa, for the kind introduction. And I'm sorry I could not be here today. I was planning to be in person, but unfortunately there was a project meeting where I had no input and I had to be here in person. So that's why I could not be in talk today, giving this talk in person. So, but I hope the Zoom talk would still be good. So I'm pretty excited about talking about this work on human in the loop learning for anomaly detection. And this is a joint work with my former PhD student, Rakibul Islam, who is a research scientist at Meta, and Shubhamoy Das, who was my postdoc. So let's look at some motivating applications. So the first application is credit card fraud detection. And here, what we are interested in is we want to look at all the transactions and figure out which transactions are unusual, and so that we can flag them. But the thing is that if we have lots of false alarms, then we are wasting a lot of human effort in terms of the people at the credit card company who deal with, every false alarm or alarm that is raised, right? Similarly, we have people who are doing ICU patient monitoring. So here, you look at all these time series charts. In fact, I had my first-hand experience when my wife was in the labor room and I was looking at these time series. And it was amazing that some of the nurses were so good at actually looking at these time series and figuring out what was going on and when they have to intervene, for example, right? But more broadly speaking, when you're trying to monitor these patients' condition using these sensor data, again, if you have a lot of false alarms, then you're wasting a lot of resources in terms of the nurses and the doctors that need to attend whenever there is actually an alarm. And this is very critical when we have people who are working in the medical domain. There is a lot of shortage of such resources. Right. Similarly, we have Android malware, right? I mean, we have so many mobile applications, and at the same time, the malwares are also increasing significantly over the years. And malwares can potentially spy, steal information, make fake calls on our behalf, especially with the recent advances in generative AI. So there is a whole anti-malware industry around this, right? So hopefully you are convinced that through these three applications and many more, the problem that we are interested in is we have basically a bunch of inputs, right? These could be images, these could be time series data, these could be credit card transactions. And we need some kind of computational algorithms and tools that would say, these data points are anomalous and these data points are normal. So that's what we are interested in. So let's look at what the main challenges are. So the main challenge is really, it's like finding needles in a haystack. So you have a lot of data and the anomalies are very, very small compared to the number of nominals. And this is typically a knowledge discovery task that involves humans because ultimately, once you say that it's an anomaly, a human needs to intervene and take some actions. So the idea here is that any anomaly detection algorithm, when it has a high false positive rate, we are wasting a lot of human resources, and we want to avoid that. And what I'm going to talk about today is how computers and humans and machine learning algorithms can work together to create a more collaborative system where By repeatedly using this computer program, humans can provide feedback and enable them to improve over time. And so that the false positive rate kind of goes down over time with training data. So let's look at quickly some prior work on anomaly detection. Much of the prior work on anomaly detection are what I call unsupervised methods, which means that there is no supervised data. I mean, these are predominantly based on some statistical assumptions that are made by these models, just based on the unsupervised data. And we are going to focus on one class of methods in today's talk, which is called isolation forest, which is the state-of-the-art method when it comes to tabular data. So the tabular data basically means that every feature that you have, you actually have a semantic meaning. For example, male, age, salary, those kind of things, as opposed to non-tabular data or raw data like images, time series, and so on. But you can always convert the non-tabular data also back to tabular data through some form of representation learning. So now the key question is, let me just move this floater. Okay, yeah. Yeah, so we have all these great unsupervised methods, and let's try to understand when and why they may not work, okay? There are three main things when they won't work. If they are making certain assumptions about what is normal data and what is abnormal data, and that is violated, then you will see lots of false positives. And similarly, if the nature and the type of anomalies are not known beforehand, this is the classic case of unknown unknowns, right? The anomaly detection algorithm has no handle on what it is looking for, right? And let's say not all the anomalies are very relevant for the tasks at hand. Maybe only some kind of anomalies are relevant. So in all these cases, when you configure the unsupervised anomaly detection algorithms I just mentioned in the previous slide, you will get high false positive rate, and you will waste the human effort that is involved to take whatever prescriptive actions you are taking once an anomaly flag is raised. So the key research question is, how can we use the human analysts efficiently to improve anomaly detection rate of unsupervised approaches? So we really want to take the advantage of the unsupervised methods, what they are offering, and then we want to endow them with some new data or input in a sample efficient manner to improve their performance. So that's where we are going. So what happens is that this anomaly detection algorithm will query, for some candidate inputs, here is a human analyst or a domain expert, and then you will say, okay, here is what I think an unusual transaction, right? And then it goes to the domain expert, and the domain expert says, well, it is indeed a anomalous transaction, and that feedback goes to the unsupervised model, and then you update the model to account for the new feedback, right? So in this way, in every iteration, one or more candidates can be given as an input to the domain expert, and the domain expert provides feedback about whether they are really anomalies or they are normal data. And that data can be used to configure or improve the performance of these unsupervised methods. So so like I mentioned, so here in this case, it's a normal data, right? Then there is another iteration. So again, you go, and then now here there is a new anomaly. So by doing this, what you're trying to do is that you're trying to discover more and more anomalies that the task really requires using the domain expert by asking a very small number of queries to the human analyst. Because again, the thing is that if you're asking too many questions to the human analyst, we are back to the same question that we started with, right? We are wasting a lot of human effort. So we really care about the human effort being a very expensive resource, and we want to minimize, the human effort. So because most of the algorithms here I'm going to talk about are somewhat isolation forest based, but they are more broadly applicable to many ensemble methods. But some of the algorithms are very specific to isolation forest. And the reason why we picked that is it's one of the state of the art algorithm and it has some nice properties. So an isolation forest is a bunch of isolation trees. So let's try to understand what an isolation tree is. So the idea is that an anomaly can be easily isolated from nominals, and the degree of anomaly is inversely proportional to the depth. So here I'm showing you an illustration, right? So this is almost like a decision tree, but the only thing is that here the feature and the split threshold that we are picking, both of those decisions are made randomly as opposed to, information gain based principles using supervised data. Okay. So all the feature selection and the split points are selected randomly. And here I'm showing you there are some nodes that are at a small depth. Those are called shallow leaves. And there are some nodes that are at longer depths. These are called deeper leaves. And the color here indicates, the red color indicates anomalies and blue color indicates nominals. And this is kind of a continuous range. So every isolation tree partitions the input space into these subspaces. So here I'm showing you that those partitions, and this is the depth colored subspaces. So you can see that there are certain regions which are very red corresponding to anomalies, and there is a lot of regions that is corresponds to blue, which is the nominal area. So node score is a function of the path length. And as I mentioned, if the node is at shallow depth, then it matches our intuition that this can be easily separated and it is an anomaly. So shorter the length, the higher the chances of being an anomaly. An isolation forest is a bunch of isolation trees, right? And you aggregate them. And it is one of the state-of-the-art unsupervised approaches. And then there are two main assumptions behind this approach. One is the number of anomalies are relatively small compared to the number of nominals, and features are distinguishable. Okay. But the main drawback of this method is that it assigns uniform weights for every subspace score. So remember, all these subspaces I showed you in the previous slide, it assigns uniform importance. And that is the main source of high false positive rate. And what we are going to talk about is how to fix it. Okay. So this is isolation forest, and this is the space partition for 100 trees. And when you do the contour plot for 100 trees, as you can see, when you have an ensemble model or this forest, the anomalous regions are very nicely separated from the nominal regions. So as you can see, the forest is kind of helping you make better decisions, all else being same. So let's look at the model definition, right? So the isolation forest generates a high number of subspaces or leaves. So every leaf node you can think about now as some kind of a feature representation, right? And the score is really the depth of, inversely proportional to the depth of the score, okay? And that means that every input you can actually assign it a huge vector that corresponds to the number of leaves across all the trees. So it will be fairly high dimensional, right? And only those leaves where this exact data point falls down, it will have a non-zero value. All other feature values would be zero. And the standard isolation forest assigns equal weights to each of these subspaces. And that's the main source of this high false positive rate, because in different domains, different parts of the subspaces might be more important or less important, and we want to learn those weights in a data-driven manner. So when it tries to make predictions, what it does is that every unlabeled input, which is a feature vector, it passes through the isolation forest and gets the corresponding feature vector, and the weights are uniform, right? So then you just add all the scores that you get, and then you rank all the unlabeled examples according to these anomaly scores, and you pick the top tau candidates as anomalies. So you're sorting according to this score, and you're picking the top ones as your anomalies, right? So the anomaly detection accuracy, like what fraction of these tau candidates are really anomalies, depends on the weights of the model, right? And the question is basically, how can we learn optimal weights so that all the top tau candidates that we are picking according to our anomaly scoring function, there is a lot of them are actually anomalies. So as I mentioned to you before, our key tool here is to use the human feedback to improve the performance of the anomaly detector. So the approach would basically say, I want this input to be labeled, and it will also have some kind of interpretation or explanation that tells basically why the approach is picking this particular input to be labeled by the human analyst. For example, it says, I'm picking this example because the credit score is low and this person is not employed. Okay. And then the human analyst looks at the record of the person and then labels it as nominal or anomaly, and that gets added to the label data that we already have. So as I mentioned, we are always using this anomaly detector with the weighted scoring function to rank all the unlabeled instances and then pick the top label, the highest scoring unlabeled example for feedback. There is some theory behind why the highest scoring unlabeled example is the right input to be queried. We have an upcoming JIR paper where we actually prove it, but that's not very important in this context, right? And so what happens is once you label that as nominal, let's say, right, and then you select the next one and you say nominal and then so on. So what would happen is you are trying to push the anomalies as high as possible according to this ranking score, and all the nominals are being pushed to the lower end of this ranking. That's what is happening here. So this is okay if you want to only label one input in every iteration, right? What if you have multiple domain experts? For example, in the context of credit card transactions, there might be multiple people at multiple offices who are all monitoring, and you want to use all of them as opposed to sequentially, you want to do some batch processing. Right. Similarly, there might be in the smart grid management, you might have multiple grid operators that are distributed, and you want to somehow make use of all of those resources to improve your anomaly detector. So the goal here is that we want to discover diverse anomalies, not all anomalies that are very similar to each other. That's not very interesting because we don't learn a lot about the anomaly space. So if you only select the top scoring ones, then all your queries will be located in a small region of the input space, which are close to each other. As opposed to, we have this diverse selection, right? And the idea here is that you look at all the labeled data and the anomalies, and you come up with some compact subspaces, and you pick the queries from different compact subspaces. Okay, and it's related to a set covering problem, and you can use an ILP formulation to solve it. So what we do is we actually exploit the inherent structure of this isolation forest because it gives you these nice subspaces. And so what we are trying to do is that from all these subspaces, how I can find compact subspaces that cover all my labeled data. Okay, and we use these subspaces to select diverse inputs by saying, well, okay, if I have a budget of B, I want to select from B different compact subspaces. And the learning goal, once we have some labeled data from the human, is to learn the weights of each of these leaves so that the anomalies are ranked higher than the nominals. This is a typical ranking problem, and there are many tools out there to learn good ranking functions, including for linear models. Okay, so what you have is you have old weights and some labeled data, right? And you have some new labeled data, and you want to learn unupdated weights, right? And the optimization to update the weights after every feedback, the nominals are ranked lower than the topmost tau fraction, because remember, we are interested in the top tau fraction of the inputs, and we want most of the anomalies to be in that list. We don't want any of the nominals to be in that list. And a small change in the weights can satisfy this constraint based on the labeled data. So here is a illustration of this approach. So as I mentioned, it's an iterative approach. So you have on time axis, you have the number of iterations and your model is changing. So here the current weights are WT, and this is the quantile for the top tau candidates. And then you are selecting the top scoring unlabeled example for labeling. And the human expert says it's nominal. And then you are trying to push that nominal below the tau quantile. Okay, so as you can see here, all the labeled anomalies are above the tau, are in the top tau quantile, and all the nominals are below the top tau quantile. Okay, and again you have now new weights, and you again select the top scoring input, and then you update the weights, and you keep moving. Okay, so as you can see, the goal of the weight learning is to keep the red points above this threshold and keep all the green points below this threshold. So now that we have understood this approach, let's see how well does it work. Okay, so what we did was we selected the completely unsupervised approach, so there is no feedback. Okay, and there are also, then we kind of used two things. One is we gave uniform weights, which is what the standard method does, and also we selected random weights, and also this adaptive method where you change the weights based on the new feedback data. And our main metric is what percentage of anomalies are discovered as a function of the number of queries. So remember, as a function of the number of queries that you're asking, you're basically asking what fraction of the queries were indeed anomalies. And the higher, the better. And we use the area under curve to actually compute which algorithm is better than another. So here I am showing you three representative results. It's abalone, thyroid, and cardiotography. And on x-axis, as I mentioned, the number of instances labeled. And on y-axis, you have the fraction of the total anomalies seen, and higher the better, right? So as you can see, the high-layered batch approach actually works significantly better. And a small amount of feedback significantly improves the accuracy. And this is because we have updated the weights, and the updated weights helps us in finding new anomalies, because now you have a better sense of what are anomalies and which examples are normal. And when we use these batch queries using our compact subspaces, we see that we achieve higher diversity, right? But diversity doesn't come at the expense of loss in anomaly detection accuracy, which is a good thing. So it's actually a win-win situation. Now, there are lots of other applications where instead of having a fixed amount of data that is stored in a database, you have streaming data that is coming in. For example, smart grid data or any kind of time series data. You have a lot of streams of data that is coming in. And the goal is still to identify anomalies from this continuous stream. There is relatively less work in this space. So as you can see here, I'm showing you the data is coming over time as a stream. So here at T1, this data came, and then T2, this data got added, and T3, this data got added. So when you have this kind of streaming data, this makes the problem even more challenging. And the main sources of challenges is we want to detect whether there is a concept drift or not, right? So the question is, what is an anomaly? Does it change, depending on the time and the data? And even in this case, when and how should I update the model? And in some cases, when the data is coming at a very fast rate, you can't actually store all of the data because of your memory constraints, right? So then the question becomes which data you want to be storing and how do you want to update the models? So here is an illustration. Here I'm showing you the time axis, and the data is coming in, right? And you have an isolation forest sitting here. And you still got feedback from the human expert, right? And you got the next time step, you got new data. You have again an isolation forest, and again you're asking feedback from the human expert, and it continues. Okay. So the first challenge, which is drift detection, right? Whether something changed in the data that requires actually updating our model. and we want to do it in a completely data distribution manner. So what we do is we compare the data distribution of the new window, which is what the time window I meant, with the old window, and then we compute what is called K divergence. And the nice thing is that the isolation forest naturally enables us to compute some form of a distribution over the data, using a non-parametric model. And this scale divergence gives you a quantitative metric whether how much the data has changed between the previous window versus the now. And as you can see here, I'm showing you two example data sets, and it seems that in these two data sets, there is not much drift was observed. Okay, whereas if you see here, there is a huge drift in the data, and this is where you need to really update the model and add more trees. So there are these two scenarios when you have limited memory and the concept drift is very small. So this problem becomes almost similar to the previous one as in batch setting. All you need to do is that you need to do a little bit of retraining with newly feedback. But when you have major concept drift, then a lot of your model is also stale. So what you need to do then is you need to replace a fraction of the older trees and include some new trees from the current window. And when you add new trees from the current window, you initialize the weights of the new trees with just uniform weights, and then which can be learned over time, right? So again, we did some experiments comparing the streaming version of the diverse and streaming version of the top, select top for querying, right? And what we see is that with feedback, the highlight batch is consistently the best performer because obviously, right? I mean, it has much more information. It sees the complete data. Whereas streaming data, it is operating with limited information because it doesn't know what data it will come in the future. And so the batch version is the upper bound in terms of performance. And what we see here is that the performance of the streaming algorithm is very close to the batch performance, which is actually a very, very good news. And updating ensembles of trees, we tried various things like 10% of the trees, 20% of the trees, and so on and so forth, just to see what would be a robust parameter here, when the concept drift is high. But we also saw that we can actually use the KL divergence metric itself to decide what fraction of the data can be, of the model needs to be updated, okay? To summarize my talk, I mentioned about the effectiveness of unsupervised ensembles and isolation forest in particular for anomaly detection. It's a state-of-the-art approach. But the problem here is that it results in high false positive rate, which means that we are wasting effort from the human analyst that is in the loop to take corrective actions whenever an alarm is raised. And what I talked about in today's talk was how the human feedback can be used to tune these ensembles to reduce the false positive rate over time. And I also talked about how we can exploit the inherent structure of the isolation forest to discover diverse anomalies without loss of accuracy. And similarly, when you have streaming data, how you can use these trees to quantify the amount of drift detection and use that quantification to update some fraction of the trees from the current model. So what we are really looking for is a human-machine collaborative system here, which improves its performance based on experience of the human using that system. And in fact, that's actually a very synergistic goal that is applicable to a lot of other applications of machine learning, data science, and AI more broadly. So there are some general principles out here that could be applied to other settings as well. So with that, I would like to thank you all for your attention, and I'm happy to take questions.
Thank you very much, Jana, for this very nice presentation. I know you traveled unplanned, and so we appreciate that you were able to make it. And I know it was probably even today that you had to go. So I'm glad that you made it, and just to let you know, we are in Town Hall 203, and all of the things that we have had so far were happening live, and your sound was better than the ones that we had live because there is a speaker, a very nice one in the room.
Okay.
So I'm going to see if there are questions for you since you don't see the room.
Yeah.
I will and relay the question, James.
Hi, Dr. Gopa. You mentioned a couple times in your talk that specific reasons why isolation force is really good in this situation. Are there some candidate models that you considered, or does isolation force blow everything else out of the water?
Yeah, we have used a lot of other models, including LODA. So like I mentioned, the approach itself is general enough, like the overall human in the loop learning is applicable to any ensemble-based models, including LODA and so on. And also, even if you don't have tabular data, if you have like image data, what you can do is that you can pass it through a deep generative model or an autoencoder to get a latent space. And then you actually train your isolation forest or some of the other existing methods in that latent space, and you can still use these ideas. In fact, we got that question when the paper was reviewed by JIR.
Yeah.
I might have misinterpreted what the slide was saying, but you mentioned adding new trees. When you have the whole forest functioning, testing anomalies of that, over time, do you eventually add in new trees and phase out old ones, or do you just add more?
Were you able to hear the question, Anna?
If you can rephrase and tell me, I would appreciate it, Asifa.
Yeah, so you had the isolation forest, and the question was, when you find new trees, are you discarding old ones from the forest because of new information the new trees have brought in, or how is the tree grow, the forest grow? Is that
Was it just, do you just add them on top, or do you also remove?
Yeah.
Are there times when your isolation forest had to remove trees out of it?
Yeah. So like I mentioned to you, whenever there is a concept drift is actually very large, then it means that our model is actually stale. So which means that we have to replace the trees, right? And what fraction of the trees would be replaced with new trees would be depends on our KL divergence based quantification about how much the concept drift is there. Excellent question.
That was a very good question. Any other questions? There are no more questions, Jana, so I think the audience will also be grateful because you would have given them a little bit more break before the next presentation. So thanks again for doing it, and it came out very clearly. Thank you.
Thank you, Asifa.